Hey, good afternoon. My name is Oleh, and I'm happy to present my master thesis slide titled Reinforcement Learning for Voltage Control-Based Ancillary Service Using Thermostatically Controlled Loads. Here is a plan for this presentation. First, I will give a short introduction into power system domain and energy imbalance management task. Then problem formulation is given along with an overview of related work. Then I shortly describe approach to solution, then experiments and received results. These are grouped in two parts, proof of concept and extensions, as well as project development was grouped. This presentation is finished with result summary and directions for future work. So what should you know about the power system domain? It is quite conservative and heavily based on analytical modeling. It has been stable for decades and has accumulated strong expertise. However, there actually are major changes in recent years. This includes wide use of IoT devices, integration of renewable energy sources, and decrease of stability margins. In these new conditions, old methods are not capable to deal with all the new challenges. At the same time, the domain hasn't benefited from the application of machine learning methods yet to a full extent. One more thing you should know is that ancillary service in the power system are all means that are used to successfully supply electricity to customers. In this project, we focus on development and ancillary service for energy imbalance management. To keep it simple, the amount of electricity generated should be equal to the amount of electricity consumed. Otherwise, instability in system appears and the system may collapse. It's intuitively clear that if generation is smaller than consumption, customers will not receive all the required energy. However, I would like to emphasize another case. When generation is bigger than consumption, maybe even worse, because this leads to damage of transportation, generation, and even customer facilities. So how is it done now? According to the related work, energy imbalance management is introduced at the level of a whole power system or its significant parts. Because of that, reaction time is not smaller than 1 minute and usually 10+ minutes. Two main methods in this direction are financial incentives and control over generator facilities. The first one doesn't ensure but just encourage demand-supply balance, while the second one reduces generators' lifespan, so they are not ideal. One more important insight from the related work is that thermostatically controlled loads are the best kind of loads for energy imbalance management. The intuition behind is quite simple. Electricity is hard to store, but thermal buffer in TCLs allows to temporarily store energy. Taking all this into account, it was decided to extend a successful attempt of energy imbalance management at the middle level of a power system with a voltage controller over a TCLs. This was done by Bogodorova and others in 2016. So here we have a problem formulation. The aim of the project is to investigate and assess possibilities of reinforcement learning-driven controller development for the purpose of energy imbalance management. Such a controller should be placed in the point of common coupling of TCLs and make a decision on voltage change, taking into account reference power level and actual power level. The control goal is to reduce difference between these two, and we use mean squared error as a metric. So, but why reinforcement learning? To answer this, first I will have to introduce you to reinforcement learning itself. Sometimes called semi-supervised learning, its main particularity is that a model, typically called an agent, is learning from an interaction with a system, typically called an environment. A control goal is set implicitly by defining a reward function. So the agent aims to learn an optimal policy by performing actions in an environment and processing a feedback. But why should we use it? The main reason is that many and arguably most problems in the power system domain are control problems, including the one considered in this project. And reinforcement learning has shown great capability to solve control problems in various domains. Most likely you've heard about reinforcement learning applications winning the game of Go or the game of StarCraft. We reviewed application of reinforcement learning in power systems and found following insights. Usually, such applications apply control at the level of a whole power system to keep it stable, or at the lowest level of hierarchy on the customer side to reduce costs. In this aspect, our project is different because we both apply control at different level and aim as a control goal. One more thing is that simple algorithms like Q-learning show reasonable results and thus are widely used, as well as straightforward continuous spaces discretization strategies. Last but not least, in power system domain, a lot of models are available for simulations. That's why they are widely used for training agents. Having all this on hand, we formulated research questions and corresponding hypotheses. First, we would like to know if it is possible at all to develop such a reinforcement learning-driven controller. And if yes, there is a need in understanding its development and application particularities, especially its generalization abilities. To answer these questions, we considered a specific power system problem. It contains 20 TCLs and is simulated with an analytical model. It also allows deterministic and stochastic TCLs parameters initialization. The last option allows to investigate actually generalization abilities of the controller. To use this model, we built a pipeline that connects a reinforcement learning agent to a model simulating an environment through the OpenAI GIM interfaces. For this purpose, Modelica GIM Toolbox was developed that finishes the pipeline. It was also presented at International EOLT workshop in Berlin, and corresponding paper was published. So finally, having this experience pipeline, we can come to experiments. Here is a diagram of experiments conducted in the first stage of a project development, proof of concept. Here we focused on defining performance of alternative approaches and application of Q-learning. In this presentation, I will focus only on main results. These are constant reference power level and stochastic parameters initialization. So first, we define performance of alternative approaches. Alternative approaches are baseline when no controller is placed in the system, and the competing approach when constant control is applied using the same controller design. We use optimal constant control by simulating by simulating the whole interval. As you can see here, competing approach is much better performing than the baseline. That's why in the project we mostly compare the developed controller to it, not to the baseline. Then we moved to application of Q-learning. Q-learning is a basic reinforcement learning algorithm that is based on a concept of Q-value. Basically, that's the main takeaway from the slide. Q-value is a proxy for how good certain action is in a certain state. Many algorithms are based on this concept, but in Q-learning, these values are estimated quite straightforward by iterative updates. When applied to this problem, Q-learning showed successful results both for constant and step down in reference power level and for different parameters initialization cases. However, it wasn't strongly superior to the competing approach. On the other hand, it showed an ability to generalize. That is an important advantage over the competing approach. Here you can see some results for the Q-learning applications, in particular, distribution of performance for developed controller and optimal constant control, that is the competing approach. Even with these outliers in the right tail, the developed controller is slightly superior in the median performance. There was a hypothesis that these outliers are caused by the transition process present at the beginning of a simulation. I will come to this in a minute. This is an example of system behavior before and after the controller training. You can see that after the controller training, actual power reference is approaching reference power level. So controller is efficient in its training. And mentioned transition process is this high peak in actual power level at the beginning of a simulation. To test its influence on controller training, we tried to exclude it from the training and testing process. On the left, you can see dependency of performance on the reference power level when transition process is included, and on the right one, it isn't. So skipping the transition process indeed led to less outliers in the right tail of performance distribution. So with these results, we basically answered the first research question. It is indeed possible to develop such an RL-driven controller. Then we moved to the second stage of a project development that is called extensions. Extensions aimed to improve performance and investigate the developed controller better. First, we applied different discretization strategies. Why do we need them? Because basically most reinforcement learning algorithms are dealing with discrete state and action spaces, while real-world applications are not. They are dealing with continuous ones. First, we applied straightforward equal width binning that is pictured on this diagram, and investigated dependency of performance of the controller on the number of bins in this approach. Then we applied other approaches, smart discretization strategies, including optimal width selection with histogram-like approaches. In particular, we applied Friedman-Diaconis estimator for estimating optimal width of a bin. We used quantiles of historic data as bin's edges and accounted for problem formulation by taking reference power level as bin's edge. The last one showed the best results among all the smart discretization strategies. However, as you can see here, these are performance distributions for different discretization strategies. All results are quite comparable between each other and to the competing approach. However, in some cases, we observe more outliers than in others. Afterwards, we decided to apply window input key learning that is providing wider context for decision-making to a reinforcement learning agent by passing window of environment states as an input. We tested several configurations. However, best results were observed for window size 1 that basically corresponds to vanilla key learning, and that's why work with this algorithm were stopped. Afterwards, we applied DQN. According to the best practices, we used experience replay and target network with it, and it showed performance comparable but not better than the key learning. Why? This should be investigated further, but this was found with observed results that there is a need in deeper investigation. Here, I would like to emphasize that we used a simple architecture to layer perceptron because our problem isn't high dimensional. Here are some results to ensure you that these results for DQN are actually comparable with the competing approach. So the final results can be summarized as follows. We achieved performance that is much better than the baseline and comparable, but not always superior to the competing approach. At the same time, we have an important advantage of generalization. The developed controller shows an ability to generalize, on the contrary to the competing approach, where we need simulation of a whole time interval to choose an optimal control. Yeah. So in the end of the project, we answered all the questions, achieved 4% improvement in median performance for some cases, also described particularities of such controller development and application, and found evidences of generalization abilities of this controller. As an additional contribution, already mentioned paper and toolbox. However, this project has a lot of directions for future work, including reformulation of a problem to provide wider context to the agent. As an example, I could come up with adding binary indicators if certain loads are on or off to the environment state. To better investigate generalization abilities of a controller, there should be considered longer time intervals and bigger number of TCLs. We also would like to investigate better other control signal change intervals. I haven't mentioned this in a presentation, but this was included in the paper. Yeah, and for sure, from the point of view of power system domain, it is important to consider our controller designs. So basically that's it. Thank you for your attention, and I would like to thank the Alex company for funding this and other research projects in the machine learning lab. I would like to thank everybody who supported and made my fellowship in the machine learning lab possible, including but not limited to Alexei Molchanovsky and Yaroslav Pritula. And last but the most important, great thanks to my supervisor, Tatiana Babydurova.
Any questions? Can you elaborate a little bit more on what exactly your controller goals environment? So it's possible for your controller to affect both generation and consumption or only generation.
As it was mentioned, controller controls voltage. It is placed in a point of common coupling of these thermostatically controlled loads, and basically it controls what voltage these loads will receive. So you have a substation at some point of your power system. There are loads that are connected to these substations, and you can control in certain interval the voltage for them. Yeah, that's it. I hope.
More questions? Yeah, can you please describe what the inputs, like you described the discretization, right? Binning strategy.
Yeah.
But like binning for which inputs?
Yeah, as I've mentioned in problem formulation, two signals are available for decision making: actual power level and reference power level. So we're discretizing actual power level and, if needed, reference power level.
Okay. Yeah. So the next question is, you mentioned Q-learning, right? And then you described like alpha star and other modern things which beat in human in some complex games. But then they don't crop bins itself. They use deep Q-learning. Maybe you can elaborate more why it didn't work. Like how much data you had, or like what's the reason behind it working?
Yeah, the first thing I would like to emphasize, I haven't mentioned that it didn't work. I mentioned that it wasn't superior to the Q-learning. So the second point is that with experiments we conducted, we observed that there is a need in basically deeper investigation. Why is it happening? In scope of this project, we made only limited tuning of these models, like size of perceptron layers, but we haven't changed the number of layers, for example. Because of that, there are two options. It's either because architecture is not complex enough to overfit, to keep it simple, or the problem itself is too simple that we don't have to apply such complex algorithms. So
they would work, right? So if the problem was too simple, they would probably outperform the order. Or stay on the same level.
If they are not confused by their internal sophisticated structure.
Yeah, okay, you'll continue discussing
Yeah,
this.
sure.
Just ask, did you consider the notion if your environment is actually Markovian, so and if you can apply reinforcement learning to it? So did you consider like what is the autocorrelation?
Yes, that's a really good point, and that's why we have to, as I mentioned in future work, to consider other problem formulations. Currently, we assume that it's kind of Markovian, and we can make a proper decision about a voltage change based only on the current values for actual and reference power level. So basically, that history doesn't matter. But it is a simplifying assumption, and for sure, there might be that it isn't totally true. About exactly your question, no, we didn't investigate it explicitly. But results showed that there might be improvements when we reformulate the problem to provide wider context.
More questions? Jump on.
Sure.
Тобто, я розумію, що презентація співака говорить про специфікацію, а чому не можна було спробувати якісь виділення конфліктів? Менше важливо, може, швидше вчилися, я розумію, що не вчилися. Чи були якісь такі щось крім працівників? Ну, може, просто там вимірні конфлікти, знову ж таки, там потім вийде, що там насправді просто не виникає, що там буде ризик, цікаві пацієнти, це можна там не
От. Власне, глибоке дослідження різних варіантів DQN не входило в скоп проекту як такий. Як я сказав, що ці результати показують, що нам треба більше попрацювати, якщо продовжувати роботу в цьому напрямку, в напрямку застосування до конкретно цієї задачі різних алгоритмів, це можливо. Але з іншого боку, коли у нас фактично вектор стану environment, середовища, має розмірність максимум 8 або зазвичай 4, то doesn't make any sense. Ну, тобто,
багато, можете прикладати, якщо взяти там одновременну конволюцію, то подивитися взагалі, що там просто може бути коефіцієнт, і це вплюс до інтерпретабіліті, і вплюс до того. Так, що там просто якась агресія, тобто, ну, можна ну, я просто, я до того, що, тобто, цікаво було подивитися, що воно там вивчило, якщо ви кажете, що, в принципі, так, ну, і цього забагато, тоді, взагалі, питання, типу, ну, а що є мінімально?
ну, в цьому контексті Q-learning є мінімальним, оскільки там все максимально straightforward. Але, звісно, дякую за цей комент, тому що це питання не досліджувалося глибоко, і оскільки насправді це ongoing project, то це дуже корисно. Дякую.
Я розумію задачу, не знаю, ми працюємо з енергетикою.
Так.
Для мене, напевно, для людей, які там всі приймають рішення в енергетиці, напевно, важливо розуміти, що там дають роботи, вони довіряються якомусь там рівному агенту. Ну, питання, чи насправді, як стоїть тут питання там інтерпретабіліті. Теж такі. Чи не може статися так, що у вас автор там в якійсь інформації просто вирішив, що ну, правильне рішення, я знаю, всім вирішили структурі. Ну,
Окей,
це
тут...
філософське питання, але я до того, що...
Ні, звісно, це практичний пойнт. Тут з точки зору загальної відповіді я можу сказати, що сам контролер дизайн з фізичної точки зору не дозволяє перформити якісь екшени, які не є дозволеними. Це по-перше. А по-друге, interpretability of results і те, як його застосовувати в продакшені, так би мовити, проводилися в дуже обмеженому скопі, просто тому, що це не була основна мета роботи. Тож, насправді, як я сказав, домен дуже консервативний і до реального застосування дуже далеко. Тут була більше ціль показати, що це можливо, і дослідити особливості цього контролера. Коли мова буде йти про те, щоб претендувати на його застосування на практиці, звісно, треба дослідити, як він вчиться. Чи можна його вчити не на симуляціях, а на реальній системі. Тому що preliminary, я можу сказати, rough estimates, що це можна робити, судячи з того, що система ніколи під контролером навіть на початку навчання не виходила з певних систем.
Тоді зразу питання, а як вона навчиться, якщо ви ставите обмеження? У вас, наприклад, було такі піки страшенні.
Обмеження на voltage, а це power, тобто потужність, consumed and generated.
Ще запитання?
Так, у мене питання, власне, коли ви говорите про можливе впровадження, чи досліджували ви питання scalability? Ви змоделювали, наскільки ви все тестили на одному середовищі?
Так.
Тобто ви збудували одну схему, там, скажімо, так, мережі. Одна мережа, і на ній ви все протестували. Правильно я зрозумів? Чи ні?
Правильно, але ця мережа має стохастично ініціалізовані параметри.
Так, але все одно вона фіксована.
Так,
То ви
звісно.
зафіксували, скажімо, там 20.
Так, звісно,
вузлів.
звісно, так.
Що буде, коли цих вузлів стане 20 тисяч?
Як я explicitly mentioned, це future work. We have to consider bigger number of TCLs to check if it works. Але для scalability в плані енергетичної системи, де ми хочемо задеплоїти декілька таких контролерів, енергетичної системи. Енергетичної
Що
системи.
нордичне. І мав інтерференцію з нордичними роботами, з регуляторними нордичними роботами на енергомаркеті. Продовжуйте.
Отже, якщо ми хочемо задеплоїти декілька таких контролерів в систему, знову ж таки, детальне дослідження цього питання не проводилося, але є rough estimates, що вони не мають бути concurrent. Тобто в тому була і суть формулювання задачі на середньому рівні енергосистеми, що ми не намагаємося контролювати одразу всю систему, ми намагаємося оптимізувати якусь частинку, не чіпаючи все інше. Відповідно, якщо ми поставимо декілька таких контролерів у різних частинах системи, вони будуть оптимізовувати різні частини, і вони не мають конкурувати за умовні ресурси. Тобто, так.
Тобто вони мають якось домовлятися за це?
Ні, в тому то й суть цього problem formulation, що ми намагаємося максимально уникнути ускладнення. Зрозуміло, що оскільки в нас є широке